Okay, so I'm going to tell about two algebraic theories, touch briefly upon it, and I hope to raise your interest to have further looks into the literature. So the first theory is called the Algebra of Communicating Processes. It's a process theory starting with axioms. And what can you do with it? One thing is base a programming language on it, and that's called SubScript, and I'll briefly show that. The other theory looks a bit similar at first sight. It's called PGA, Program Algebra. Also axioms, and you can do, it helps you reason about some puzzlers that you can encounter in programming, like with Java static variable initializations. And both theories have in common that have been invented or co-invented by Bergstra, who is a researcher based in Amsterdam, in the Netherlands. And afterwards I will give a small conclusion. So this algebra of communicating processes, what is it? It's a bit like Boolean algebra. But in ACP, things can happen. It's not just statements that things are true or false or whatever, but things can happen. So basically we have an OR operator and an AND operator, like in lots of algebra, but the AND operator is now a sequential operator. It's AND then. And this way there is a kind of notion of time or so. And that becomes important because now there's not just true and false and so on, but there is also things that can really happen in time. They're called atomic actions, and we denote them A and B. And the role of true and false or 0 and 1 is that 0 is now a process that can never happen. It's deadlock. That's what we call it. And 1 is a process that succeeds immediately. And if you start from this, then you can add things like parallelism, defined in terms of sequence and choice. And you can also define communication, synchronous communication between processes, disruption and interruption. And there are even extensions to this theory with time and space and probabilities and money. It's the ACP was developed starting in 1982 by Bergstra and Willem Klop in Amsterdam. And predecessor theories that you may have heard of are CSP and CCS, which were developed around 1978 or so. So these five axioms of ACP, these are called the basic axioms. You have them also in the Boolean algebra. There are a bit more about negation. So initially there's no negation in ACP. And there are also axioms for these 0 and 1 elements. And what can you do with these? Well, you can use these axioms also as a term rewrite system from left to right. So now we can compute what would happen with such a term, x plus 1 and then y. So what would happen? First, we write the rule that can apply. Is this distribution law? So then we would get x and then y, or 1 and then y. And we can further simplify the 1 and then y. And we get here x and then y, or y. In other words, here x has become optional by adding just 1 to it in the sequence. So you can express things like parallelism, like x parallel y means is then defined using an auxiliary operator, left merge operator. It says, well, either the x process starts first and then the rest is parallel with y, or y starts first with an action and then the rest is parallel with x, or they can start with communication. And then you can define all these other processes, or these left merge operator and also the communication operator, using some more axioms. Now, what can you do with the theory? You can reason about things and prove that there is a deadlock in a parallel system. In practice, that works, but it is quite hard. So there are some papers written about it, and it's not really easy stuff. Personally, I use the ACP in an easier way, just as a formalism to express these things like choice and parallelism in a more basic way. And last year I was here at Lambda Days, and I presented this example, among others. And I'll briefly touch upon it. Suppose you have to create a GUI controller for a simple program. There's a search text field where you can type thing, and then you can say go, and then somewhere in the background, on Google for instance, a search happens, and at some point the thing returns. And if you want to program this in Java Swing, then you must be sure that everything happens in the right thread, and that's quite hard. So what happens in Java is your code looks like this. It's really ugly, and what happens, it's kind of spaghetti. So we should not want to write these kinds of programs. In this language, SubScript, which is an extension to Scala, you write, well, for instance, here the life of this GUI controller. It's a search sequence, etc. These three dots mean something like while true. And the search sequence, it starts with a search command. And then we show some text. We do the search in the database and we do some search results. And it's just a sequence. On the other hand, the modes of operation are different. The search command happens. It's a kind of listening. It's an event that happens from the outside world. So searching text and the results is something that must happen in the GUI thread. And searching in the database must be done in the background thread. But you can quite easily specify this. Search command, you can just say it's a search button. Well, in the Scala style, this is in fact a kind of implicit call to a script that says the search button is being clicked. So, this is kind of a shorthand notation, but what happens here is so you must click the search button. The searching text is an action. It's done here using a piece of Scala code between a special kind of braces. And there is an annotation which says that it must run in the GUI thread. The annotation is not really part of the language, but the language allows for some tweaking in this respect. And to do something in the background thread, we have a different kind of braces with asterisks. And now you can easily extend the program. For instance, if you want to have a cancel option and an exit button, and you must also be able to use the enter key, for instance. So again, we have an eternal loop of search sequences. And the search command is a search button, but now we can also add the enter key. That's an OR operation. Both things work. And we are not really adding processes together, but we are adding things. And through this implicit conversion mechanism of Scala, it's applied to processes. But basically it says a command is, it goes through the button or the key. Likewise, the cancel button and the exit command, well, it's by the exit button or the window closing button on top of the window. And now exiting, what does exiting do? So you start with an exit command, then you get this "Are you sure?" dialog, and if you're sure, then it's done. But if you're not sure, for exiting, you must press the exit button or again. And you get the dialog again. So it's a kind of eternal loop. It's modeled this way. So we have a sequence of an exit command. Then we do in the GUI thread, we run this confirmation dialog. And then with a kind of dataflow construct, the result of the confirm exit is fed into the while predicate. And this works. And now we have to activate this exit process. And that's by placing it in parallel with the main script. And this is not, in SubScript, it's not normal parallelism. This is kind of OR parallelism, which says that the entire process is ready as soon as the left-hand side or the right-hand side is ready. It's a bit like you have in Scala and Java and C with the Boolean OR operator, but it's more symmetric. So the search sequence will never end, but the exit process will end at some point. Now you can add more things. I won't go much into it, but well, let's say for canceling, there's a similar operator, which is a slash, which means disruption. So you can cancel an ongoing process by, in this case, by another event. So far for this ACP and what you can do with it. This PGA, it's a bit similar theory, and you can, it's kind of a computational model. I would say the alternative, maybe an alternative for the Turing machine. And let's have a quick look at this. So it's again built with atomic actions, but now these atomic actions result either in true or false. And spatial operators are a plus A and a minus A action, which perform these atomic actions, but also do a small jump. So plus A will, when true, it will execute the next instruction, and otherwise it will skip the next instruction. And minus A, similar, but the other way around. And there is also a termination instruction and a relative jump forward. And that's all there is. And then you can reason about these things and say programs are built of these primitive instructions, and there is a sequential composition. And you can even have an eternal, there's also notation for an eternal iteration of these things. So again, there are these kind of axioms, and it's very typical for the work of Jan Bergstra. So it always starts with axioms and then proves that it's always sound and so on. And he gives some laws. You have a loop unfolding, which can be proven by use of these axioms. So I won't dive into this, but the style is completely similar to ACP, I would say. Then, this is a very low level, but you can go higher, make higher levels out of it. For instance, we had only forward jumps, but we can define backward jumps in terms of these forward jumps in higher levels. And on still higher levels, you can have numeric labels and go-tos to those labels, and even if, then, else, and while constructs. Then Bergstra reasons about what is a program. He says, well, a program is just defined relative to a programming language, and a programming language is just a set of expressions and a projection to this program algebra. It's a definition, it's not a theorem. And what can you do with it? There's a nice paper, Projection Semantics for Multi-File Programs. And here you have these kinds of, this applies for, this uses a structure of projections, which are also, you can see this also as a kind of compilation steps. And what can you do with this? For instance, if you have 3 Java class source files, what happens when you are doing strange things with static variables? Now, the first file says we have a main program, and it calls a method in the second file. And the second file has 2 static variables, and a third as well. So, and in practice, these things are very hard to reason about if you just think in terms of Java. But by hand, you can translate this into program algebra on a high level. And looks a bit strange at first sight, but this is the essential stuff, what happens there. Then you can go one projection lower, you can project it to one level lower, and then basically you are getting rid of these method calls. And this is one thing, and at this level you can already reason what will happen with the variables, what value they will have after initialization. Okay, well, this is Jan Bergstra who created these theories. And I took, in 1980, course, mathematical logic from him at Leiden University. He also taught lambda calculus during this course. So he created this ACP. In the 90s, he started to think about Java. What does it mean? What does a Java program do? He couldn't find it out. And then he developed this program algebra. And later he made also some other nice theories. A few years ago, he became head of the informatics section of the European Academy of Science. So he's recognized as an important scientist. Yet, these theories are widely unknown. ACP, okay, there is, for ACP there's some acceptance, but PGA is, only very few people have heard of this. Okay, and that's, I think that's a pity. At the same time, it could be a kind of nice successor for a Turing machine. What I miss in these PGA publications is whether it's really a kind of Turing machine. I'm not sure. I asked Jan Bergstra, I said, yes, it should be. So, I would bet my money on it. But there are lots of opportunities in this area. So if you're working in a university or for teaching students or so, I would certainly recommend to dive in these materials. So by clicking on my page at the conference site, you can click to the PDF of this with these slides. And at the last page, I have lots of references for you. So I hope you will enjoy mainly, for most also PGA. It's a very nice theory in my view. Thank you very much for your attention. Is there a relation to functional reactive programming? I'm not completely sure. So with this SubScript, I'm trying to program the same things like in functional reactive programming. And I don't use things like promises and futures and so on. But you can have implicit conversions to those to futures. But what happens, I'm not completely sure where it is. So on one hand, these scripts look like parser combinators. And on the other hand, they have also some things in common with futures. One thing that you gain is that these processes are really interruptible or disruptible, and in the future not currently. So that's one bad thing of futures. On the other hand, you will lose some performance here. In many cases, it's not very bad. So the typical processing speed is 10, maybe 50,000 actions per second, which is quite good for GUI controllers, but not good enough for text processing, lots of text processing, for writing a compiler, for instance. Yeah.
So you mentioned that the first thing you talked about was similar to CSP and CCS.
Yes.
Can you give a somewhat more detailed comparison than that?
Yes.
I mean, CCS and CSP are both widely known and very useful in a wide range of applications.
Yes.
Why on earth would I want to use this instead of them? When is this
So why is ACP better, I would say, than, when is it better?
Is it always better? Is that what you want to claim?
I'm not completely sure, but ACP is always better, but it was inspired by both CSP and CCS. One limitation of especially CCS is that it has not a real sequential composition. There's action prefix. So the left-hand side of a sequence must also always be in a single action. And about 10 years ago, a bit longer, Jos Baten has written a paper showing that this limitation is not really necessary. So, it's very important in a normal programming language that you can really compose bigger things than just atomic actions in terms of sequences. So that's the limitation of CCS. I thought CSP has a similar limitation, but it also has another different sequential composition. CSP, what I don't like there is there are two different choice operators, exclusive choice operators. And in practice, when I use ACP, the ACP style when writing programs, I only need one choice operator. So that's different, but the real different approach between ACP on the theoretical level and CCS and CSP is that CCS, CSP, they start with, this is the world, and we see these laws for the world. And ACP started with the laws, and then they can build different models, so finite processes and infinite processes, and with and without recursion, whatever, and they can study each different kind of world also. But first they can derive laws that hold in every world or model that they can construct based on the axioms. And that's the algebraic approach. And about 1990, the groups of CCS and CSP, they found out, well, this algebraic approach is nice, and then they called themselves also process algebra. That was the working name for ACP up to then. So they said, oh, we also have process algebras, and they were widely known. And then the Amsterdam people had to rebrand their name into ACP, because otherwise it would kind of disappear in a way.
Thank you.
Yeah.